Just as we grow old and die, so do our cells. So our tissues are constantly replenished with new cells. That's useful in places where cells are lost, such as the insides of our blood vessels. When old cells die, neighbor cells can divide to fill the gaps. But as we age, this process slows down, and it can eventually come to a halt. Cells can divide only so many times before they simply can't reproduce themselves anymore. This may be the ultimate timekeeper for human beings. A cell is in some ways like a candle. When there's nothing left to burn, the light is gone. This burning wick is not simply a metaphor. On the end of every chromosome is a bit of DNA. It's a simple sequence repeated over and over. It's called a telomere, and it plays a vital role protecting the end of each chromosome and keeping it healthy. Like the wick of a burning candle, telomeres get shorter over time. When a chromosome divides, it loses a bit of the telomere on the end. The enzymes that build DNA simply can't work on the very tip of a chromosome.
There's a gradual loss of these telomeres from the ends of the chromosomes. Each time the cell divides and creates a new set of chromosomes, a little bit more of these telomeres are lost each time. Eventually you get to a state where the telomeres no longer function to protect the DNA, and they gum up the cell, if you will. I mean, they stick together, they stick to the walls of the nucleus, and it becomes impossible for the cell to keep dividing.
When cells can no longer divide, the clock of life grinds to a halt. The next step for that cell is death. Here in Dallas, Texas, some scientists think that this process plays a central role in aging. So they are avidly studying the telomeres as Ponce de Leon searched for the fountain of youth.
We know that aging is genetic. We know that aging runs in families, that people who have parents that live into their 90s, generally they live into their 90s, and there are other families where individuals always die in their 50s or 60s. And so we believe that part of that might, in fact, be due to the telomere length that you were born with.
Jerry Shea wonders whether it might not be possible to rebuild telomeres, giving cells a new lease on life. He's studying an enzyme called telomerase, which can make short telomeres long again.
If you think about our telomeres as being the gas tank in an automobile, and that when we're born, we have a full tank of gasoline, and as we age, we use up the fuel, and when we're old, we're basically running on empty. And so telomerase is essentially like adding fuel to the tank to keep the car rolling.
The genetic blueprint for telomerase is on chromosome 5. This enzyme is able to slide along a strand of DNA and extend the length of telomeres. When telomerase is present, cells can keep on dividing indefinitely. Telomerase is only supposed to work in an embryo. Cells early in our life have to divide many times in order for a human being to grow from a single cell. Telomerase keeps that process going. What would happen if we were able to tap the power of telomerase to keep our cells growing and dividing indefinitely? Would that extend our lives? Would we become immortal? It's certainly not that simple, but the fountain of youth may not be an impossible quest.
it is probably going to be much more complicated than fixing a gene here and there if you're really going to talk about prolonging human lifespan to a significant extent. Not to say that in 30 or 40 years we won't see the arrival of some clinical trials trying to see whether the normal lifespan can be extended to some degree. But the notion that we will achieve biological immortality still seems very far out of reach. I think the death rate will continue to be one per person for quite a long time to come.
We may never see the day when the aging process is stopped, but even slowing that process to expand the human lifespan to 110 years or maybe 120 years has profound implications for a planet that's already struggling under the burden of its 6 billion human inhabitants.
If we ever unravel the molecular process of aging, we'll be faced with the question of, should we intervene in the process? Should we make small molecules that delay aging? Should we ever contemplate gene therapies that would produce people who age more slowly? I think these are deep and important questions. They're not fundamentally scientific questions. They're social questions, not to be answered by scientists alone, but by the